Hello, and a warm welcome to this tutorial on autonomic nervous system function analysis. We'll be focusing on how to use Kubios effectively to analyze data from standard autonomic nervous system tests, so let's get started. In this video, we're going to walk through the standard tests used to evaluate autonomic nervous system function. These include the Valsalva maneuver, deep breathing, and the head-up tilt challenge, often referred to as the Ewing tests. We'll be breaking down each of these tests and demonstrating how to analyze the data obtained. First, we'll cover how to access the analysis tools within Kubios and the prerequisites for performing these tests. Then, we'll examine each test systematically. We'll demonstrate the measurement procedures, typical signal and analysis samples, and finally, the report generation and interpretation of results. It's important to note that the results of autonomic nervous system function generated by Kubios HRV are intended for informational purposes within a professional health and wellness context, and are not for clinical diagnostic use. Before diving into the analysis, let's talk about how to get access to the ANS function analysis within Kubios HRV software. To access the features of autonomic nervous system analysis, a license for the full scientific version of the software is required. Licenses can be obtained directly from our website. Furthermore, accurate beat-to-beat heart rate data is essential. This necessitates the use of a heart rate sensor that supports this functionality. A convenient and reliable solution is to utilize the Kubios HRV mobile application in conjunction with polar heart rate sensors, such as the H10 or Verity Sense. Okay, let's begin our examination of ANS function tests with the Valsalva maneuver by exploring its characteristic heart rate response and its connection to overall autonomic nervous system function. The Valsalva maneuver involves the subject performing a forced exhalation against a closed airway, typically into a mouthpiece, to generate a sustained pressure of 40 millimeters of mercury for 15 seconds. This controlled maneuver provides valuable insights into autonomic nervous system function by allowing us to observe the characteristic heart rate response during and following the pressure phase. During the initial phase of the Valsalva maneuver, heart rate typically increases due to heightened sympathetic nervous system activity. This sympathetic response is initiated by a transient reduction in aortic blood pressure, a consequence of the increased intrathoracic pressure diverting blood away from the heart. Immediately following the forced exhalation, heart rate may continue to rise briefly. This subsequent elevation is influenced by both the natural inspiratory reflex, which induces vagal inhibition, and the somewhat delayed response of the sympathetic nervous system. Subsequently, heart rate decreases as a result of a rapid rise in blood pressure. This blood pressure elevation activates baroreceptors, triggering parasympathetic cardiac activity. The increase in blood pressure is attributed to the return of blood to the heart as intrathoracic pressure normalizes, and also partly to residual sympathetic activity causing peripheral vasoconstriction. It is essential to mark only the exhale phase of the Valsalva maneuver with an analysis sample when analyzing the data in Kubios HRV Scientific. On this slide, you can see a typical heart rate response to the Valsalva maneuver. The Valsalva ratio is calculated as the quotient of the longest RR interval, measured within 0 to 30 seconds following the maneuver, and the shortest RR interval, measured during or within 0 to 5 seconds after the maneuver. To improve precision, the ratio is computed using 5 beat average values for both the longest and shortest intervals. In Kubios HRV software, the Valsalva ratio is presented using a 4-zone model, which is based on reference values for healthy adults. The zones are very low, low, normal, and high. A Valsalva ratio within the very low zone is considered abnormally low for healthy adults across all age groups. Younger adults, specifically those under 40 years of age, are expected to exhibit Valsalva ratios within the normal or high zones. Now, we'll move on to the second test, the deep breathing challenge. We'll explore how this maneuver elicits a characteristic heart rate response, providing further insights into ANS activity. The deep breathing challenge requires participants to maintain a respiratory rate of 6 breaths per minute, equivalent to 0.1 Hz. This controlled breathing pattern should be paced using either a metronome, another suitable pacing device, or a pre-recorded deep breathing pacing video. For example, the one on our YouTube channel. You can find the link in the description. During inhalation, heart rate increases. This acceleration occurs because the diaphragm contracts and descends, expanding the thoracic cavity and reducing intrathoracic pressure, which facilitates air intake. The resulting decrease in arterial blood pressure leads to baroreceptor deactivation and a reduction in vagal tone, ultimately increasing heart rate. Conversely, during exhalation, heart rate decreases. This deceleration happens as the diaphragm relaxes and ascends, compressing the thoracic cavity and increasing intrathoracic pressure, which expels air from the lungs. The consequent rise in arterial blood pressure activates baroreceptors, enhancing vagal tone and thereby reducing heart rate. As a result, a healthy individual's heart rate shows clear modulations synchronized with the breathing cycle, accelerating during inhalation and decelerating during exhalation. These fluctuations can be easily observed, even through manual pulse palpation at the wrist during deep breathing exercises. Place the analysis sample between the beginning of the first inhale and the end of the last exhale. To evaluate the heart rate response to deep breathing, we identify the longest RR interval at the end of expiration and the shortest RR interval at the end of inspiration. These intervals are then averaged across the respiratory cycles performed during the challenge. The heart rate response is quantified as the difference between the maximum and minimum heart rates, expressed in beats per minute, calculated from the averaged RR interval extrema points. Alternatively, the response can be reported as the difference or the ratio between the averaged RR interval extrema. In Kubios HRV software, the heart rate response to deep breathing is presented using a 4-zone model, based on reference values for healthy adults. A heart rate response within the very low zone is considered abnormally low for healthy adults of all ages. Younger adults, specifically those under 40 years of age, are expected to exhibit a heart rate response within the normal or high zones. Finally, we'll examine the orthostatic test, the third and final maneuver in our autonomic nervous system function assessment. We'll explore how this test elicits a characteristic heart rate response, providing further insights into cardiovascular autonomic regulation. The third standard autonomic function test evaluates the heart rate response to orthostatic stress, commonly induced by a head-up tilt. This test can be conducted through an active tilt, where the participant transitions from a supine to a standing position. It's crucial to ensure the participant does not experience a fall due to potential orthostatic hypotension during this active tilt. Alternatively, a passive tilt can be performed, utilizing a tilt table to move the participant from supine to upright. To ensure accurate assessment of heart rate and heart rate variability, both the supine and upright positions should be maintained for a minimum of 5 minutes. Let's explore the autonomic nervous system's response during this test. In the supine position, the body is at rest and parasympathetic tone predominates. Consequently, heart rate is typically low and heart rate variability is elevated during supine rest. The head-up tilt induces a significant gravitational shift of blood from the upper body to the abdomen and lower extremities, resulting in a reduction of central blood volume. This leads to a decrease in cardiac output and blood pressure. To counteract this abrupt drop in blood pressure, the sympathetic nervous system is activated, resulting in an increase in heart rate and peripheral vasoconstriction. Following the tilt, heart rate gradually increases, peaking approximately 15 seconds post-transition. Subsequently, a new baseline is established as the sympathovagal balance stabilizes. In the upright position, the mean heart rate is elevated, and HRV is reduced, particularly in indices sensitive to parasympathetic activity, compared to the supine position. You need to create 2 analysis samples in Kubios for this test. Create 1 analysis sample for the supine position and 1 for the upright position, leaving the transition between the positions unmarked. Ewing et al. Observed in 1985 that heart rate typically reaches its maximum around the 15th beat following the transition to an upright position, followed by a relative bradycardia, leading to a local minimum around the 30th beat. The ratio between the longest RR interval around the 30th beat and the shortest RR interval around the 15th beat is defined as the 30-15 ratio. In Kubios HRV software, the 30-15 ratio is presented using a 4-zone model based on reference values for healthy adults. A 30-15 ratio within the very low zone is considered abnormally low for healthy adults across all age groups. Younger adults, specifically those under 40 years of age, are expected to exhibit a 30-15 ratio within the normal or high zones. Various HRV parameters can be evaluated to examine autonomic function changes during the transition from supine to upright. The supine position provides baseline heart rate and HRV values during spontaneous breathing. The parasympathetic nervous system index should decrease, reflecting the reduction in HRV associated with parasympathetic activity due to the postural change. Standard time domain and frequency domain HRV parameters can further elucidate the change in ANS function. Specifically, the low frequency, LF, and high frequency, HF, spectral components of HRV are valuable in assessing the shift in sympathovagal balance. However, it's essential to ensure that the respiratory rate is within the HF band, and the software's validated respiratory rate estimate is useful in this regard. Let's summarize this video. ANS function analysis involves assessing how the autonomic nervous system regulates body processes, like heart rate, blood pressure, and breathing. ANS analysis helps understand the balance between the sympathetic and parasympathetic branches of the ANS, providing insights into stress response, relaxation states, and overall health. With the Kubios HRV software, you can easily and accurately calculate the standard ANS function parameters, such as the Valsalva ratio, HR response to deep breathing, and the 30-15 ratio for head-up tilt. If you want more information about Kubios HRV software and enjoy educational content on heart rate variability, subscribe to our channel and follow us in social media. Thank you for watching.